You're likely familiar with the term downforce if you've watched even a bit of Formula One. It's not just jargon. Downforce is one of the most critical forces in the sport, responsible for making these cars stick to the track as they reach mind-blowing speeds. But what exactly is it, and why does it matter so much? Downforce is a vertical aerodynamic force that presses the car down toward the ground as it moves through the air. It's essentially the inverse of lift in an airplane. Instead of soaring into the sky, a Formula One car is pulled harder into the tarmac. At around 150 kilometers per hour, an F1 car generates enough downforce to match its own minimum weight, around 795 kilograms. At maximum speeds, that force multiplies more than 5-fold. That's like having several full-grown adults pushing down on the car at all times, giving it more grip through corners and helping the tires bite into the track surface. To maximize this invisible yet powerful force, F1 teams focus intensely on the car's aerodynamic profile. The front and rear wings play a major role, as does the car's floor. But the truth is, every surface that touches the air contributes. Engineers meticulously manipulate these components to work together, crafting a harmonious flow that boosts performance while minimizing disruptions. The wings in particular are tools for controlling how much downforce a car can generate. On high-speed tracks with long straights, the wings are flat and minimal, slicing through air with less drag. But on tighter circuits filled with sharp turns, they're larger and angled more aggressively to turn airflow into downward pressure. That pressure helps the car maintain control through demanding corners. But there's a catch: drag. As downforce increases, so does the resistance working against the car. Drag is the aerodynamic enemy of speed. The more surface area the car exposes to the wind, the more it gets pushed back. That resistance eats away at top speed and fuel efficiency. It's why every element of an F1 car is sculpted like a high-speed dart. Every curve, every angle is designed to minimize drag without sacrificing grip. Even the end plates and cascade elements on the front wing help direct air around the tires and under the chassis to reduce turbulence. It's a precise dance of physics and design. To gain a competitive edge, F1 introduced a revolutionary system in 2011, DRS, or Drag Reduction System. With the push of a button, drivers can open a part of the rear wing on designated zones of the track, flattening it to reduce drag and increase straight-line speed. This creates better opportunities for overtaking. However, it's not a free-for-all. During a race, drivers can only activate DRS if they're within 1 second of the car ahead at a designated detection point. That opens the rear wing flap, letting air flow through more freely, boosting top speed, and closing the gap before a corner. Once the driver hits the brakes, the wing snaps back into place, restoring downforce for stability. It's a clever way to balance the need for close racing with the demands of aerodynamics. While wings and body panels shape the air above, the real magic happens underneath. Enter ground effect. This principle returned to Formula One in 2022 after decades of absence. Ground effect takes advantage of the airflow beneath the car to create a low-pressure zone that sucks the car downward. The shape of the undertray and diffuser is critical in this. As air rushes under the car, it accelerates through narrower channels, lowering pressure and increasing grip. This vacuum effect drastically improves stability and cornering performance without the drag penalty of large wings. And because it leaves less turbulent air behind, it also allows trailing cars to follow more closely, improving race quality and creating more overtaking opportunities. But even ground effect doesn't escape the complexities of what F1 engineers call dirty air. That's the turbulent wake left by the car in front, which disrupts the airflow for any car trying to follow closely. Dirty air makes it harder to generate consistent downforce, robbing the chasing car of grip. It's why following too closely used to be a major disadvantage, until new rules and designs began addressing the issue by cleaning up airflow patterns and redistributing aerodynamic load more evenly across the car's surfaces. Ultimately, Formula One is a battle of aerodynamic efficiency. It's a constant quest to balance drag and downforce. Reducing drag helps with straight-line speed. Increasing downforce improves grip through corners. The trick is doing both at once without sacrificing one for the other. That balance changes from track to track. On some circuits, engineers favor a low downforce setup with minimal wing angles for top speed. On others, they dial in maximum downforce for tighter corners and better braking zones. Every race is a new puzzle. One way to maximize performance without overhauling the car design is through slipstreaming. When a car follows closely behind another, it tucks into the pocket of air the lead car has already sliced through. This reduces drag for the trailing car, allowing it to accelerate faster and potentially make a pass. It's a technique used across racing, from F1 to cycling. And while it's simple in concept, it's hard to master. In qualifying, drivers can even use a teammate to tow them down a straight and gain precious milliseconds. But in the race, it's a calculated risk. Move too late or too early, and the slipstream vanishes. Or worse, puts you into turbulent air that ruins your lap. Modern F1 cars are marvels of aerodynamic engineering. From downforce and drag to DRS, ground effect, and slipstreaming, every element is about bending the wind to the car's advantage. Engineers spend thousands of hours in wind tunnels, simulations, and real-world testing to chase the perfect balance. And even when they get it right, they start over for the next race. Because in a sport where hundredths of a second matter, air is everything. But it's not just about going faster, it's about controlling chaos. Every lap in Formula One is a battle between physics and control, where turbulence, temperature, tire wear, and wind direction can all shift the outcome. The cars may look smooth from the outside, but inside, the air is violent. Engineers have to manage that invisible war, channeling pressure zones, reducing instability, and carving out performance where no one else has. It's why the shape of a barge board or the angle of a rear wing can make or break a team's season. Every piece of an F1 car serves a dual purpose. The floor isn't just a surface, it's a vacuum chamber pulling the car down. The diffuser isn't just an exit ramp for air, it's a sculpted tunnel to control expansion and turbulence. Even the mirrors, wheel covers, and brake ducts are shaped not just for function, but to steer airflow exactly where it needs to go. There's no dead space. Every inch is designed to manipulate air in ways that translate directly into speed, grip, or balance. And that's before the race even starts. During competition, drivers and engineers are constantly adjusting settings in real time to react to track conditions. Brake balance, differential settings, energy harvesting, and aerodynamic load can all be tweaked from inside the cockpit or through pit wall strategy. It's like solving a Rubik's Cube while skydiving, with wind speeds changing every second. As F1 moves into the future with sustainability goals, synthetic fuels, and cost caps, the role of aerodynamics will evolve yet again. The challenge isn't just to build the fastest car, but the most efficient one that performs under new limitations, with fewer resources, and in a more eco-conscious world. That means smarter wings, cleaner shapes, and perhaps entirely new aerodynamic systems we haven't seen before. Formula One is not just about engines and tires. It's a symphony of air, pressure, and design, played at over 300 kilometers per hour. It's where science meets speed, and where perfection is constantly being redefined. The cars may be built in factories, but their true form is shaped by wind. Subscribe to Rev 2 Riches for more high-speed stories from the cutting edge of automotive design.